You're shopping for storage and suddenly it feels like you're decoding military radio signals. SATA, M2, PCIe, NVMe, TLC, Gen 4, Gen 5. One drive costs $40, another costs $300. They look almost identical, and we've all hovered over that buy now button wondering if we're about to make a very expensive mistake. So what's actually different? And more importantly, what actually matters? Today we're breaking down everything you need to know about SSDs, what they are, what all those acronyms mean, what truly affects performance, and how to choose the right one without wasting money. Let's start simple. SSD stands for solid state drive. Unlike a traditional hard drive, which stores data on spinning magnetic platters and uses a moving mechanical arm to read and write information, an SSD uses flash memory with no moving parts. That one difference changes everything. With a hard drive, every time your system needs a file, a physical arm has to move to the correct location on a spinning disk. That movement takes milliseconds. An SSD, on the other hand, can access data electronically almost instantly, often in microseconds. That's why even a basic SSD feels dramatically faster than a hard drive. It's not just about top speed, it's about latency and responsiveness. Boot times drop from minutes to seconds. Programs open immediately. The entire system feels snappier because there's no mechanical delay. But here's where confusion begins. Not all SSDs perform the same, and the differences come down to 4 layers: form factor, interface, protocol, and NAND type. Once you understand these 4, every SSD on the market suddenly makes sense. Form factor is simply the physical shape of the drive. The classic 2.5-inch SSD looks like a thin laptop hard drive and connects with a SATA cable. These are still extremely common and work in almost any desktop or older laptop. They're reliable, widely compatible, and still perfectly usable today. Then there's M2. This is where people start assuming things. M2 isn't a speed upgrade. It's just a haircut. It looks fast. That doesn't mean it is. An M2 drive is that small, gumstick-sized piece of storage that plugs directly into your motherboard. It removes cables and looks modern. But here's the important part. An M2 drive can run either SATA or PCIe. So buying M2 does not automatically mean you're getting maximum performance. It just means you're getting a compact form factor. There are also less common formats like U.2, which looks like a 2.5-inch drive but runs over PCIe and is often used in enterprise systems, and add-in card SSDs that plug directly into a PCIe expansion slot, like a graphics card. For most consumer builds, though, you'll be choosing between 2.5-inch SATA and M2. Next comes the interface, the road the data travels on. There are 2 main consumer interfaces, SATA and PCIe. SATA has been around for years and was originally designed for hard drives. The current common version, SATA 3, tops out around 550 megabytes per second in real-world speeds. When SSDs first appeared, that was a massive leap over hard drives that averaged around 100 megabytes per second. But today, SATA isn't slow. It's just not winning any races. It's still perfectly fine for office work, web browsing, general use, and even storing games, but it has a hard speed ceiling. No matter how advanced the flash inside is, the interface itself becomes the bottleneck. PCIe, which stands for Peripheral Component Interconnect Express, is a much faster connection standard, the same type used by your graphics card. PCIe uses lanes, typically X4 lanes for SSDs, allowing data to travel in parallel. Each new generation increases bandwidth per lane. PCIe Gen 3x4 delivers around 3,500 megabytes per second. Gen 4 doubles that to roughly 7,000. Gen 5 pushes toward 14,000 megabytes per second under ideal conditions. But here's something important. Your motherboard and CPU must support the generation you're buying. A Gen 4 drive placed in a Gen 3 slot will simply run at Gen 3 speeds. PCIe is backward compatible, but you won't unlock higher performance without compatible hardware. Now we get to protocol, the language the drive uses to communicate with the system. AHCI, or Advanced Host Controller Interface, was developed long before SSDs became mainstream. It was designed around the needs of spinning hard drives and supports only a single command queue with up to 32 commands at a time. That was perfectly adequate for mechanical disks, but SSDs are capable of handling far more simultaneous requests. NVMe, which stands for Non-Volatile Memory Express, was built specifically for flash storage. Instead of one small queue, NVMe supports up to 64,000 queues with 64,000 commands per queue. In simple terms, AHCI is one checkout line at a busy store. NVMe opened every register and hired extra staff. That dramatically reduces latency and allows SSDs to operate at their full potential, especially under heavy multitasking or professional workloads. NVMe runs over PCIe, which is why NVMe drives are significantly faster than SATA drives. AHCI is tied to SATA, so when you see NVMe SSD, it means you're getting the faster protocol combined with the faster interface. Now let's talk about what's actually inside the drive. NAND, flash, memory. This is one of the most overlooked but important differences between SSDs and NAND cells. Store bits of data, and the more bits stored per cell, the cheaper but slower and less durable the drive becomes. SLC, or single level cell, stores 1 bit per cell. It's extremely fast and durable but very expensive and mostly used in enterprise environments. MLC, or multi-level cell, stores 2 bits per cell. It offers strong durability and performance but has largely been phased out in favor of higher density options. TLC, or triple level cell, stores 3 bits per cell. This is the most common consumer SSD type today because it balances cost, speed, and endurance well. QLC, or quad level cell, stores 4 bits per cell. It reduces cost, but also reduces endurance and sustained write performance. Many QLC drives rely on a fast temporary cache. When that cache fills up during long file transfers, performance can drop significantly. QLC drives are perfectly fine for everyday use. Just don't ask them to sprint a marathon. Endurance is often measured in TBW, or terabytes written. This rating estimates how much data can be written before the drive's cells begin to wear out. For most normal users, even QLC drives will last many years. But if you're constantly writing large video files or running intensive workloads, endurance becomes more relevant. Now let's talk real-world performance. For gaming, the difference between a SATA SSD and a high-end PCIe Gen 4 NVMe drive is often smaller than marketing suggests. Load times may improve, but we're usually talking seconds, not dramatic leaps. Where NVMe truly shines is in large file transfers, video editing, 3D rendering, running virtual machines, or compiling massive projects. Generation 5 drives pushing extreme sequential speeds are impressive from a technical standpoint, but a Generation 5 drive won't magically turn your PC into a NASA supercomputer. Most users will never saturate that bandwidth in everyday tasks. Faster isn't always noticeable. Sometimes it's just measurable. So what should you actually buy? If you're upgrading from a hard drive, even a SATA SSD will transform your system. If you're building a modern gaming PC, a PCIe Gen 3 or Gen 4 NVMe drive using TLC flash is usually the sweet spot. If you're a content creator working with large media files, prioritize a quality Gen 4 NVMe drive with strong sustained performance and good endurance. If you're on a tight budget, QLC can be perfectly fine for general use, as long as you understand its trade-offs. Common mistakes include assuming M2 automatically means fast, overspending on Gen 5 when Gen 4 is more than enough, ignoring motherboard compatibility, or buying the cheapest QLC drive for heavy professional workloads. At the end of the day, SSDs aren't complicated once you separate the layers. Form factor is the shape, interface is the road, protocol is the language, and NAND type is the engine. Put those together and the alphabet soup becomes logical. You don't need the most expensive SSD on the shelf. You need the one that actually matches how you use your computer. And now, you know exactly how to choose it.